小关系，这是第3课的课文 Reading。你只要大声的读1遍就好了，只要大声的读1到2遍就可以了。现在先不用写考题，也不用看懂，就是课文跟题目各大声的念1到2遍或2到3遍。Reading 3呢，我们一共有75行，我们看这边有75行，一样啊。妈妈会把这个copy在那个Google 的翻译里面，你要跟着它大声的念，你先不用读懂没有关系，就是要大声的念几次课文。
As any good contractor will tell you, a sound structure requires stable materials. But atoms, the building blocks of everything we know and love, bowling balls, bridges, and best friends 5, don't appear to be models of stability. Why are some atoms, like sodium, so hyperactive while others, like helium, are so aloof? Why do the electrons that inhabit atoms jump around so strangely, from one bizarrely shaped orbital to 10? Another? And why do protons, the bits that give atoms their heft and personality, stick together at all? Has a tiny nucleus containing positively charged protons 15. And uncharged neutrons, swarmed by a cloud of speedy electrons. We are also told that like charges, such as protons, repel each other with a force that shoots up to infinity as they get closer. Even worse, you can't get much closer 20 than 2 protons in the nucleus of an atom. So what's keeping atomic nuclei from flying apart? Obviously, some other force must be at work inside the atom, something that we can't detect at our human scale. Physicists call this the 25 strong nuclear force. But where does it come from? For the building of protons in the nucleus, it must have certain interesting features. First, it can't have any 30 sizable effect beyond the radius of the atom itself, or it would play havoc with the nuclei of adjacent atoms, destroying matter as we know it. Second, it must perfectly balance the repulsive force of electricity at an equilibrium point of about 35. 0.710 minus 15 meters, the average distance between bound protons, in order to create a stable nucleus. Third, it must repel at even shorter distances, or else neutrons, which don't have any electrostatic repulsion to balance the strong nuclear force, 40, would collapse into each other. The graph shows the behavior of such a force relative to the repulsive electrostatic force. Japanese physicist Hideki Yukawa proposed that the nuclear force was covered by 45. A then undiscovered heavy subatomic particle he called the pi meson, or pion, which, unlike the photon, which conveys the electrostatic force, decays very quickly and therefore conveys a powerful force only over a very short distance. 50. Professor Yukawa's theory, however, was dealt a mortal blow by a series of experiments conducted at Los Alamos National Laboratory in the early 1990s that demonstrated that pions carry force only over distance greater than the 55 distance between bound protons. The pion was a plumber's wrench trying to do a tweezer's job. Suggests that the strong nuclear force is most likely conveyed by massless particles called gluons, according 60. To the theory of quantum chromodynamics, or QCD for short. According to QCD, protons and neutrons are composed of smaller particles called quarks, which are held together by the aptly named gluons. This quick binding force has 65, a residue that extends beyond the protons and neutrons themselves to provide just enough force to bind the protons and neutrons together. If you're hoping that QCD ties up atomic behavior with a tidy little bow, you may be just 70. A bit disappointed. As a quantum theory, it conceives of space and time's tiny chunks that occasionally misbehave, rather than smooth predictable quantities, and its mathematical formulas are perhaps as hard to generate it as the 75 nucleus itself.